A student investigates the relationship between force and acceleration for a trolley on a runway. Figure 12 shows some of the apparatus the student uses. So we've got the typical bench, this F equals MA practical. We've got a truck or trolley with a card on it, a light gate to measure the speed or acceleration. Light gates can be hooked up to a computer to measure all sorts of things. So here, acceleration presumably. And what we've got is a weight or a mass hanger. We add masses to this. It provides a pulling force down, and that will cause the trolley to accelerate forwards, and we can vary the mass by putting masses on here of the trolley. So we can experiment, or we can we can basically practically experiment with the F equals ma equation, Newton's second law. This is a required practical, and it's very, very popular, so it's good to learn it. Describe how the student could increase the accelerating force applied to the trolley. Describe. So that's easy. This is where the force is applied over here. So by adding more mass to the mass hanger, we increase the force. So add weight or mass to mass hanger. Easy. This next question is very odd. Describe how the mass of the moving system can be kept constant. It's a very strange question. It wouldn't surprise me if anyone really got this right. But you have to say transfer the mass from here to here, so between trolley and hanger. So in other words, you can play around with the mass and change the mass here or change the mass here, but to keep the overall mass of the moving parts of this experiment, so this moves and this moves, you must transfer the mass between them, so overall the mass doesn't change. It's not particularly relevant to the practical, and I kind of wonder why they put it in there. Explain how the student could improve the procedure to compensate for the effects of frictional forces acting on the trolley. This is pretty easy. Friction, whenever you think of friction, think of adding oil to lubricate the wheels or runway, and this will reduce the effects of friction. You could also lift up the runway, put it at an angle slightly, so it's easier to overcome the frictional forces. Figure 13 shows two objects Q and R before and after they collide. So this is about momentum and changes in momentum. The arrow shows the direction of movement of the objects. The arrows are not to scale. Explain how momentum is conserved in the collision. So this is the first thing we're being asked to do. Explain how momentum is conserved in the collision, and use Newton's third law and Newton's second law in your answer. They need you to appreciate here that Newton's second law can also be written as change in momentum divided by time equals force. So firstly, let's just unpack that, because that's a straight, it's often not taught in classrooms very clearly, this. So let's understand. Well, if you remember Newton's second law, you better know as F equals ma. Now, if you think about it, another way of saying that is F equals mass times a change in velocity, so the change in velocity over time, because that is an acceleration, a change in velocity over time. Now, a change in momentum is mass times velocity, and a change in momentum would be mass times velocity minus another mass times velocity, which is basically this. Okay? And then if we divide that by time, then we're back to basically this. So you can see that F equals ma is the same as change in momentum divided by time. This is quite a tricky question to get full marks on, because it's not very obvious how to answer it. So Newton's third law, let's start off with Newton's third law. Newton's third law states that action force and reaction force are equal and opposite. So in other words, when this collides with this, they exert an equal and opposite force on each other, which is why they both move. So the force of R on Q, in other words, the force of this on this, is the same as the force of Q on R, or the negative force of Q on R. Remember, one force will be positive, the force acting in the opposite direction will be negative. You could have expressed that in the other way around, that'd be fine. The collision time for both the objects is the same. They experience that force in the same amount of time. So the collision time for both those objects is the same. So if the force is the same, if they exert the same force, and the collision time, the time of which it takes is the same, then the change in momentum must be the same. There's no way this can be different if this is going to be the same for both those figures. So we're talking about Newton's third law and linking it to Newton's second law equation over here. So using Newton's second law, change in momentum divided by time equals negative change in momentum divided by time. What this means is we're talking about the law of conservation of momentum. So momentum is always conserved. So when this collides, the momentum that was in this one will be conserved in the momentum in this one. So the change in momentum divided by time will equal the negative change in momentum divided by time. So there's no overall change in momentum. So we've used this formula, Newton's second law, to explain why momentum is conserved. It'd be hard to get full marks on this question, but as long as you're talking about the third law and second law, and you're talking about momentum being conserved, you will pick up marks.